Welcome to this lecture on measurement uncertainty. In this lecture, we're going to cover a number of topics. Number one, we're going to talk about why we want to analyze uncertainty. Secondly, we're going to talk about the types of measurement uncertainty. Third, we'll talk about how to estimate that uncertainty. And then we'll lastly finish off talking about how to express that uncertainty. And then in a different lecture, we'll talk about the propagation of that uncertainty through calculations. So let's get into the material. If you take a look at the screen here, the picture here obviously is of a terrible accident, a locomotive that has gone a little too far. This really isn't a case of uncertainty, or if it is, it's a gross negligent uncertainty. It's more of just a mistake someone made, but it's a dramatic photo, so I thought I'd show it here. All right, let's get into the material. First of all, why analyze measurement uncertainty? Well, first of all measurements have some uncertainty to it. Even computational results have some uncertainty to it. The input parameters into those computations have some uncertainty, and that gets propagated through to the final result. So every measurement isn't just a number, it's actually a number that has a range. You know the true value of that number within some range, and that range is expressed by the uncertainty attached to that measurement. So let's just jot that down. All measurements have uncertainty. And we need to report that uncertainty so people know how confident we are actually in the measurement. So let's take, for example, the following situation. Let's say we had a plot x and y, and we had some data points. We have 3 data points that look like that. Let me just duplicate it over here because we're going to look at it twice. So let's say in one case, we make measurements very carefully. They still have some uncertainty to it, but the uncertainty is relatively small. So our uncertainty in this case, let's say, looks like that. Now, the bars there, the vertical bars, just mean that we know the real value of that measurement. The real value of y is somewhere in that range, that vertical range. The dot on that picture is just it's just the average of the measurements we made in that particular range, or the middle of our measurement range. But we know the real value is somewhere in the middle there. We don't know exactly where within that vertical bar the real value lies, but we know it's somewhere in that bar pretty confidently. In that particular case, you could say, oh wow, well y has some sort of linear trend with x. It looks something like that. You could put a best fit through line through that, and you could say, it has that kind of slope with reasonable confidence. Now on the right hand side, with those measurements, let's say we were very sloppy and we had large ranges of uncertainty. So now the range within which the true value lies is much larger, right? We don't know exactly within that vertical bar the measurement lies. So if we were going to try to put a trend on here, it could go something like this, possibly, or it could go something like this, or it could even go something like that. We don't know. The measurement uncertainty is so large, we don't know where the real value lies in that range. So we're much less confident in that data, and we can draw fewer conclusions from it. The uncertainty is too large to really have confidence in the data itself. So putting the uncertainty along with the data values is very important, so we know how much confidence to have in those actual numbers. Okay. Let me give you another example of where it's handy to have expression of uncertainty. Let's say we wanted to compare an experimental result to a theoretical result. So let's say we have a measurement of mass flow rate. So we're measuring the mass flow rate of water from a faucet. And we do this experimentally, and we measure the mass flow rate is 1.6 plus or minus 0.3 kilograms per second from the faucet. Okay, so let's say that's our measurement. And we have a theoretical prediction. We use some model and we do a prediction of that. And that theoretical model tells us that the mass flow rate should be, let's say, 1.8 kilograms per second. So if we look at that for a moment, you'll see that the theoretical prediction lies within the uncertainty of the experimental measurement. So it's very possible our model does a good job predicting that mass flow rate. It's certainly within the range of the uncertainty. So our theory, we could conclude that our theory is consistent with the experimental data. It gives us confidence in our theory. However, if the experimental uncertainty was instead of 0.3, let's say it was 0.1 kilograms per second. In that case, the theoretical prediction lies outside of our experimental measurement. There we would not have as much confidence. We'd have little confidence actually in our theoretical measurement. It doesn't lie. Our theoretical prediction is outside where the true measurement lies. So we don't have very much confidence in our theory there. So again, reporting the uncertainty gives us tells us how much weight to give to that data. Okay, so we can make comparisons like I've just described here. Lastly, we can use experimental uncertainty to help us design our experiments. So uncertainty analysis is useful for experimental design. Obviously, with any experiment, you want to generate accurate data and precise data. You want the uncertainty in your experimental measurements to be very small. And one of the things you can do is when you design the experiment, you can do an uncertainty analysis to it. And we'll talk more about that later in this lecture and mostly in the next lecture. But you can see which parts of your experiment generate the most uncertainty. And then you can focus your efforts on trying to improve that part of your experiment so you reduce the overall uncertainty in your result. So an uncertainty analysis on your experiment and your analysis can help you improve the quality of your data. Okay, so lots of reasons why we want to measure, why we want to do an uncertainty analysis on our measurements. Well, let's now talk about the types of uncertainty that we typically encounter in practice. The first one are blunders. Now, this really isn't an uncertainty. These are just downright mistakes. Blunders are things that shouldn't happen if you were paying attention to the design of your experiment or the operation of your experiment. So an example of one blunder might be you're measuring pressure. You've got a number of different pressure gauges, and you just look at the wrong gauge. That's a blunder. You just made a mistake. You looked at the wrong gauge and wrote down the wrong number. So that's an obvious blunder. If you were paying attention, you shouldn't have made that mistake. One that might be a little more subtle is, let's say you have your pressure gauge, and it has a poor temporal response time, meaning the needle on the gauge moves back and forth slowly, but your actual experiment, the thing that you're measuring the pressure of, maybe that fluctuates very rapidly. And you're trying to measure the rapid fluctuations in the real system, but your measurement device is just too slow to respond. So that's another type of blunder. You should have, if you were careful, you should have recognized, my gauge just responds too slowly compared to the real life thing. I need a different kind of gauge. So that's a less subtle blunder, but it's one that you could have caught had you thought about it a little bit further. Another even more subtle blunder would be an example of, let's say you're trying to measure the temperature of a cavity, like you've got some enclosure and you want a very sensitive temperature measurement of it, and you use a thermometer and you stick the thermometer inside that cavity and you make your measurement, but by putting the thermometer into the cavity, you're conducting some heat out through the stem of the thermometer, and then you thus change the result of your experiment. Okay, so that is a very subtle blunder, but it's one, again, if you had given some thought to it, you could have avoided. So blunders are things, they're just mistakes that shouldn't happen. So let's make a note of that. So blunders are errors caused by inattention, like reading the wrong gauge, or poor experimental design. These can be avoided. Okay, so we won't say anything more about blunders because they should just be avoided. They're not part of our uncertainty analysis. It's presumed that you've designed your experiment well enough that you've been able to avoid those kinds of things. Let's move on to the next one. The next one is systematic or fixed uncertainty. This is an uncertainty that if you make multiple measurements using the same device, all those measurements will be off by the same amount. A good example of this would be, like, for example, a ruler that's been kind of worn down on the end. So it's not measuring the exact correct length, but it's always off by the same amount. because the end is kind of worn down. Maybe it's worn down a millimeter, so all your measurements are off by a millimeter. The way you correct systematic or these fixed errors is through calibration. You take your ruler, you put it against a well-known length, some sort of standard length, and then you see what your ruler tells us. Let's say the standard length is 1 meter, but your ruler reads it as 1.05 meters. You would know that your measurements are all going to be off by 0.05 meters. It's systematic. It shows up every time you use that ruler. So systematic errors can be resolved or fixed through calibration. Okay, so let's write down some notes here. So systematic errors, these are where your repeated measurements are always off by the same amount. Again, kind of like the blunt ruler, and these can be fixed via calibration. Another example of calibration you might be familiar with is if you were using a weighing scale and you wanted to just verify that your weighing scale was accurate. You would take some masses that are well known, so you can buy calibration masses where the mass is very precisely controlled. You put it on your weighing scale, put 3 different kinds of masses on there, see what your weighing scale gives you, draw a line through that, and that's your calibration curve. So calibration is done pretty much in every experiment in order to eliminate these kinds of systematic errors. Now, systematic errors affect the accuracy of your measurement. What I mean by that, and you've probably heard this before, the difference between accuracy and precision. Accuracy is just how close you are to the real result. So systematic errors affect the accuracy of your measurement because all of your measurements will be away from the true value because of some offset, right? Precision is how closely grouped repeated measurements will be. So they may not be accurate, they may not necessarily be close to the real value, they could or maybe not, but all of your measurements have a close grouping, they're all very close to one another. That is precision. So precision affects the scatter of your data, accuracy affects how close you are to the true value. So systematic errors affect the accuracy, and again, you can remove those systematic errors through calibration. So I'll just make a note here, affects measurement accuracy. And there's a nice little example of systematic errors over on the left-hand side. You see these rulers. I got this off the internet. Someone had gone out and purchased different rulers over the course of many years, and they were just curious to put them side by side to see what kind of measurements they have. And they took this photo, and you can see that there's quite a bit of difference between these rulers. So here is 27 inches. This one is about, it looks like an 1/8 of an inch different than the ruler on the bottom, and all of these have differences in their measurements. So here is a good case where you would have systematic uncertainty or this kind of bias in your measurement because one ruler is shorter than the other one. Now, which one of these is the most accurate, you can only determine through calibration. Measuring a well-known length and then seeing which one is the most accurate in that measurement. All right, we're not going to talk about systematic errors in our in the rest of the lecture as well because systematic errors you can presumably correct for by doing calibration. Where we will spend all of our time is really dealing with random uncertainty, and as the name implies, random uncertainty is due to unknown factors. When we make the measurement, it's not the true value, and we don't know why. It's just some sort of an effect that we can't really figure out. If we could figure it out, we could remove that unknown effect. Since it's random, we just don't really know. And so we can't systematically remove random errors. We just don't know what's causing them. Random uncertainty affects precision. In other words, when we make our measurement, the points get scattered because of this randomness. And if we have small random uncertainty, then our measurements are all tightly grouped together we get very repeatable kinds of measurements. If we have a large random uncertainty, then there's a lot of scatter in the data. The points are all over the place. Ideally, we try to reduce the random uncertainty so that we keep our data closely together. That's hard to do because you don't really know why the measurements are all over the place. So anyway, random uncertainty affects precision, and that's really where we're going to focus most of our efforts here in this the rest of this lecture and going forward. We're going to talk about how we quantify this random uncertainty and how we express it, and then how we propagate that random uncertainty through the rest of our calculations. So that's what we're going to be spending our time on. All right, so let's talk a moment about how we estimate the uncertainty. Well, the way we estimate uncertainty depends on the kind of experiment we're running. There are two different kinds of experiments that we typically perform. One is a single sample experiment. That's an experiment where you just take one measurement. And then the other kind of experiment is a multiple sample experiment where we take a bunch of measurements. And the way we estimate the uncertainty is different for each kind of experiment. Now, in a single sample experiment, we only get one shot at it. You might have a single sample experiment because it's too time consuming to gather a bunch of measurements. Maybe it's too expensive. There's a variety of reasons. Okay, but regardless, we get one measurement and that's it. So we don't have repeated measurements and then use those repeated measurements to figure out what the scatter in the data is and what the mean value might be, etc. We don't have that opportunity with a single sample experiment. You just get one measurement. So let's make a note of that. Measurement is made just once. And the way we quantify the uncertainty in that single sample experiment is it's equal to plus or minus 1/2 the least count of the experiment. So let me explain what that is. The least count is the smallest discernible division in your instrument. Like if you had a ruler, for example, if it was in millimeters, the least count, if the smallest scale division was in millimeters, the least count would be a millimeter. Okay, and we'll talk about it's usually that plus or minus 1/2 the least count. Sometimes it's a little different, and I'll explain that in a moment. Let's just go ahead and make a note of this. So the uncertainty is usually plus or minus 1/2 the least count of the device. The least count, let me put this on a different line. The least count of the measurement device is the smallest scale division. Okay, so let me go back to this example of the ruler as you see on the screen here. So this ruler, you can see, has a least count of 1 millimeter, meaning that it's hard for me to draw this, but the divisions here are 1 millimeter. So what's the least count for this ruler? It's 1 millimeter. It's the smallest scale division that we have on our instrument. So what's the measurement uncertainty using this ruler? Well, in this case, it'd be plus or minus 1/2 the least count, which would be plus or minus 1/2 1 millimeter, or plus or minus 0.5 millimeter. When we measure something, we're not going to be any more accurate than plus or minus 1/2 millimeter. That's, our scale doesn't go any smaller than that, so it's hard for us to get a more accurate reading from our ruler. So that's why we use the plus or minus 1/2 of the least count. So let's see, what's the length of this yellow box? Let me zoom in on it. Over here, we've got this aligned with this end. And over here, it looks to me like it's lined up right about here, which would be about 3.6 centimeters. So what's the length of this yellow box? The way we would report it would be 3.6 plus or minus 0.5 millimeters. That's how we would report that measurement. It could be 3.55 millimeters or 3.65 millimeters, somewhere in that range. I don't exactly know precisely what it is. If I zoom in closely, let me erase my mark. It looks like it's actually maybe a little bit more than 3.6 millimeters if you look closely at that. I just can't tell very accurately. So I just know it's somewhere in that range between 3.55 and 3.65 millimeters. So that's how we report that uncertainty. Let's do another example. Let's say we have this stopwatch, this electronic stopwatch. You operate it, with your thumb. And what is the least count for this stopwatch? Well, if you look at this for a moment, you'll see that it goes down to the hundredths of a second. So the least count for this would be 0.01 seconds, right down to the hundredths of a second. So then what is the measurement uncertainty using the stopwatch? Well, you would think that it'd be plus or minus 1/2, 0.01 seconds, or plus or minus, try to write that a little better, 0.005 seconds. You'd think that would be the proper measurement of the uncertainty, but if you did that, you'd actually be wrong in this case. This goes back to why I say the uncertainty is usually plus or minus 1/2 the least count. In this case, certainly the instrument can get down to the hundredth of a second, but we're not good enough to operate it down to that accuracy, because when you're measuring the speed of something, you have a reaction time, and your reaction time is roughly about 1/10 of a second, right? You can do this experiment at home. If you have someone hold a ruler, let's pretend this is a ruler, and you put your thumbs right, or your fingers right here, and then they just drop it and you catch it. And where you catch it on the ruler, you can see, how far it drops before you catch it, and then you can do calculation, just, how fast or how far something drops as a function of time. It's just the ballistic equation. And so you can back out what your response time is from that. And what you'll find is that most people have a response time of about 1/10 of a second. So when you use that stopwatch, the real least count is about 1/10 of a second. It's not what the instrument can do, it's what you as the operator can do using that instrument. So this is not the right measure of the uncertainty. The uncertainty would be plus or minus 0.1 seconds, because you're only able to do it to about a 1/10 of a second. So our uncertainty really should be plus or minus 0.05 seconds. So this again goes back to this idea of the uncertainty is usually plus or minus 1/2 the least count. You just have to be careful when you look at it that you take into account the whole system and not just the instrument. Okay, so same sort of thing with a ruler. If you had a ruler that was very precise, let's say this ruler had divisions down to the micron. Okay, well, you can't see that well, right? You can't see down to individual micron divisions. So even though the instrument could go into with the least count of microns, you can't see it that well. So you're going to have to base the least count on what you feel confident in. And the usual rule of thumb is you want to be 95% confident. How do you know 95 or 96%? What that means really is you want to be pretty confident that you know the measurement down to whatever you think the proper least count should be. So like dropping the ruler, even though the stopwatch can go to 1/100th of a second, you're pretty confident you can only do it to 1/10 of a second. So that should be your least count. All right, so that's how we handle single sample uncertainty. It's pretty straightforward in those cases. Multiple sample experiments get more complex, and there's a lot of statistics involved in that. So let's go on to that case. So multiple sample experiments. An example of this would be, let's say we want to measure the temperature of a container. So here's my container, it's this box, and then we have a thermometer that we're going to make the measurement. So one way you could design that experiment would be you would have, let's say 20 containers, 20 identical containers, 20 identical thermometers, and you run all of those each one time, so you get multiple measurements. Now, that's one way to do it. It's not very practical. More typically, you take the same experiment and just run the experiment multiple times. Right? So we'd have one container, one thermometer, and we just perform our experiment multiple times, 20 different times, and we get 20 different measurements from that. Regardless of how we run the experiment, we're getting multiple measurements. Okay? So the thing with random uncertainty is if it's truly random, then the distribution of our measurements will follow a normal or Gaussian curve as shown in the picture here. So you've probably heard the idea of a normal or Gaussian, or sometimes it's called a bell curve, and it has this shape shown in the picture here. This is called a probability distribution, the way it's plotted here. Let me explain a little bit the features of this kind of curve. You'll see that it's symmetric about this middle point. This middle point is the true mean of the the mean of the distribution. We'll just call it mu. I'll come back to that in just a moment. And then you'll see that they have these tails that go off to the sides. If I plotted, this axis, let's call is the x-axis right here, and then we'll say this is the value of our function as a function of x. Just call it p. P's are what's called a probability. If I plotted what this curve looks like, it actually has this form up here that's an exponential. Mu, again, is right in the middle. It's the mean of our distribution. X is our value, on the x-axis. Sigma squared is called the variance. So let me put some names here. So mu is defined as the mean. Sigma squared is defined as the variance. These are just names associated with the features of this curve. And if you take the square root of that variance, then you get what's called the standard deviation. You probably know these terms already. You've had some experience with this perhaps somewhere else, but we'll just review it. So just some features on this curve. First of all, if I integrated this curve as I go from minus infinity to infinity, the area under the curve is 1. So the area, the red, if you added the red area, the yellow, green, yellow, red, if you added all those areas up, that would equal 1. So that's a feature of probability distributions, is the area under the curve is always equal to 1. The reason they do this is because it normalizes it. We know that any kind of function that's a probability distribution will always have the area underneath it equal to 1. Okay. The other feature here is you'll see these different areas. The one feature of the normal distribution is that if you go out from the mean plus or minus 1 standard deviation, remember sigma here, sigma squared is our variance, and if you take the square root of that, you get the standard deviation. But if you go plus or minus 1 standard deviation from the mean, 68%, roughly 68.2% of all your measurements will lie in that range. And then if you go plus or minus 2 standard deviations, 95.4% of those measurements lie in that range. And then 3 standard deviations, 99.7% lie in that range. So the vast majority of your measurements lie within plus or minus 3 standard deviations from the mean. And again, if you have truly random uncertainty in your measurement, if you make the measurement many, many, many times, let's say you run the experiment 1,000 times, and you plot the how many measurements that you get of a certain value. So let's say you're measuring the value of x 1,000 times. I'll have a very small number of x measurements up here or down here, and I'll have a very large number of x measurements right in the middle here. And we're going to use this feature of the normal distribution to try to get a good estimate of the true mean of our distribution. Mu here is sometimes called the population mean or the true mean. So let me just put that in parentheses. True mean or population mean. And it's going to be a little different from what we call a sample mean. Okay, so we'll come to that in a moment. Same thing for the variance. This is the true variance or population variance. Same sort of thing with the standard deviation. True standard deviation or population standard deviation. You only know the true mean and true standard deviation if you have an infinite number of measurements, which of course we don't have, right? Or you have the function as shown here. If you have a theoretical function, then you of course know what the true mean and true variance are. But if you're doing experiments and you have 10 experiments, you don't really know the true mean because you don't have all the points to fill in that distribution curve. So you don't know it very with much confidence. So let me talk a moment about something known as the sample mean, or the sample arithmetic mean. That's down here. We'll give that the symbol x bar. That's the mean that you're used to using. It's the kind of the average that you've seen many, many times. The sample mean is just you sum up all your measurements. So xi here are your measurements that you've made. Like if we were measuring the temperature in all those cavities, if you measure it 20 times, you have 20 different temperature measurements. So these are all the different measurements. N would be the number of measurements you made. That would be the 20. And then, of course, you add those together and divide through by the total number, and that gives you the sample mean. Now, the sample mean is not the true mean, because we don't have, they would only be the same if you had the whole population, like an infinite number of measurements. Then you would know the true mean exactly. But normally when you perform an experiment, even though it's a multiple sample experiment, it's still a finite number. So you might run your temperature measurements 20 times. That's not enough to figure exactly what the true mean is. So we call this a sample mean. It's an estimate of the true mean. It's not exactly the true mean. It's just it's a value that's pretty close perhaps, but not exactly the same. And then we also have here the sample variance, and we're going to give that the symbol s squared. It's not, so we don't use a mu here and we don't use a sigma here because they're not the same as the true mean or the true variance. These are the sample means and the sample variance. So the sample variance, or if you take the square root of it, that gives you the sample standard deviation, is just our measurement minus the sample mean. So this is the deviation from our average value. We square it so we don't have to worry about plus or minus with our, when we take the deviation, they'll all be positive. We add all those together and we divide through by 1 minus the number of samples minus 1. And that will give us the variance. The variance gives us a measure, or the standard deviation, whichever way you want to look at it. That gives us a measure of the breadth of our distribution. So if I go back up to our picture here, if I had a large variance or a large standard deviation, this curve would be very broad. It'd be very broad. If I had a small variance or small standard deviation, it'd be a very narrow curve. So the variance, the larger the variance, the more widely distributed our measurements are. The less precise our measurements would be because they'd be spread out quite a bit. The smaller the standard deviation, the more precise our measurements are. They're all grouped very close together. Okay. So let me give you an example here. Let's say we take 7 measurements over here. So here's our 7 measurements, and our measurements are given by this value here. So we measure the first time, we get a measurement of 99.36. We measure the second time, it's 121.02, so on and so forth. So we run this is our multiple sample experiment. We run it 7 times. We get these 7 measurements. Now the way I got these numbers, just so you know, is I actually sampled from this probability distribution up here with a mean of 100, a true mean of 100, and a standard deviation of 20. So I just pulled randomly from that kind of distribution. So that's where these numbers actually came from. Now normally you wouldn't know that, but I'm telling you now so that we can do a comparison of our sample mean and our true mean. So now let me go ahead and calculate our sample mean from those measurements, and we'll get 108.44. And if I calculate our sample standard deviation, it's 18.49. Now you'll see that these values are not the same as our true mean and our true standard deviation. They're a little different, right? They're not exactly the same thing, and that's because the only way to make them exactly the same is if we could sample our entire population, or make an infinite number of measurements. Then we would have a much more accurate prediction of what the true mean and true standard deviation are. But since we're only sampling 7 times, we just didn't get very accurate results. Okay, this is just what we get. And in fact, if you make the measurement, and let's say we repeat these 7 measurements a bunch of times. So in our particular case, we ran it, we'll call it trial 1. These numbers are the same numbers as these over here. Okay, so I've just repeated them with our sample mean and our sample variance and standard deviation. Now let's imagine that I did the experiment again, trial 2. I get another 7 measurements. That's given right here. And you'll look and see that, wow, well, that sample mean's different. That sample standard deviation is different. And then let me do it a third time. I get this one. Still another different mean value, another different standard deviation. And I just keep repeating it. And imagine I do that a lot of times. So I just showed 6 trials, but imagine I do it 100 times, maybe 500 times, okay? And then let me plot the distribution of those means. So what I'm going to do is I'm going to plot the distribution of these values, the x bars. And if I do that, I'll get this plot over here on the right-hand side. The blue values here are the frequency with which certain values show up. So on the horizontal axis, it may be a little hard to see, these are our x bars from our 7 measurements. Okay, so these values down here are these values going across the sample means. So you can see if I run these trials, just do a whole bunch of them, I'll have very few that give me a value of about 119 or 118. That sample mean doesn't show up very often. But I do have a bunch that show up pretty close to 100. Somewhere I get a bunch of measurements, a bunch of sample means that are between 100 and maybe 102. That occurs pretty frequently, right? So if I run that experiment many, many times and calculate the sample means, I get a curve, I get a distribution that looks like that. And it turns out that curve is also a normal distribution. And I've shown that here with this kind of orange line. That's a normal distribution using the mean of the trial means. So you'll see the mean, if I took the mean of these means, this gets kind of confusing here, but if I took each of our sample means and I found the mean of those, that actually, if I did it enough times, would give me the true mean. So you can see our distribution is sort of centered about that. And then I'll get some standard deviation associated with our true means, and we call that the standard error of the sample means. So that's this quantity up here on the left side, standard error of the sample mean. It's given by S sub x bar, just to indicate it's like the standard deviation of the sample means. Okay, the language here is, you have to pay very careful. It's very careful attention to it because it's very precise. So it's the standard error of the sample means. And that, okay, so I actually report it down here, standard deviation of the sample means. The formula for the standard error, we're not going to derive it here, but it's given approximately by the sample standard deviation divided by the square root of the number of measurements. So for example, the trial that we ran, in our particular case, we're only doing trial 1, remember. These trial 2 through trial 6, etc., those are imaginary trials. Just imagine I did it multiple times. But really, in our experiment, we only do trial 1. So our standard error is approximately equal to the standard deviation of our trial divided by the number of measurements. In our case, the number of measurements is 7. So it'd be 18.49 divided by the square root of 7. And that value comes out to be about 7 here, 6.99. That is the standard deviation associated with this orange curve. So that can be derived, that can be shown to be the case. We're just going to accept it here as fact. Okay, so this is important for us, and you'll see this in a moment. So what that does is it tells us, okay, when we run our experiment here, our trial 1, and we got the sample mean, we know that, so our value actually, let me put it here, 108. 108 is somewhere like around here. So that's where our measurement was. It's somewhere in that point. Remember, we're still trying to estimate what the true mean is here. Well, we know that the true mean will lie somewhere within this kind of orange curve. Okay, so we can use our sample mean in addition to this standard error to try to put bounds on where the true mean lies. Okay, so we're going to talk about that more in just a moment here. So I think it's very important at this stage to just maybe stop the video and think for a moment about the differences between the true mean, the sample mean, a standard deviation of our measurements, just within one trial, and what the standard error of the sample mean represents. So I want you to think about all these things because they're important to understand how we're going to express our measurement uncertainty for multiple sample experiments. Okay, let's continue on then. So before we can express our uncertainty in our measurement, we need to talk a moment about a thing known as a confidence interval. So let's go back to our picture of the normal distribution that looked like this. Remember, 68.2% of our measurements are within plus or minus 1 standard deviation, and so on and so forth. Well, in engineering, we typically like to say that when we report a measurement with some uncertainty, we want to be about 95% certain our true value lies within the stated range. So when I said, for example, a mass flow rate measurement was 1.6 plus or minus 0.1 kilograms per second, what I mean by that is I'm 95% certain the true mass flow rate lies within 1.5 and 1.7 kilograms per second. I'm about 95% certain. I'm pretty confident. Not 100% certain. The true mass flow rate could lie outside of that. But if you were a betting person, you would lay odds that, yeah, it's going to lie within the range I've expressed. So in our picture here, what that means is that we want to be within plus or minus about 2 standard deviations roughly. It's actually, to be exactly 95%, it's 1.96 standard deviations. So we want to be within this range of our true mean. Okay. So let me go back to our set of measurements. Recall our picture here. The blue histogram data just comes from running this experiment multiple times. Okay, and this is the distribution of our sample mean values. Okay, so to get the true mean, I want to make sure that we're within plus or minus 2 standard error of the sample mean values from our true mean. This is a little confusing to say this, but remember, this is the standard error right here that we calculated back up here. It's the standard deviation of the sample means. So we want to be within plus or minus 2 values of that. So for example, because we know 95%, roughly 95% of our measurements will lie within that range, right? So let's see if I've got it down here. Yeah, let me kind of show it down here. Here is where I didn't draw this in the right spot. Let me do it back up here instead. So we said our measurement was about 108, right? So going back up to our picture, our sample mean was 108.44. So that's where our sample mean was located. And then if I go out plus or minus 2 standard errors from that, I'll be 95% certain that the mean is located in that range. So if I went out, the standard error, remember, we calculated was about a value equal to a 7. So that would put me pretty close. So 2 times 7 gets me 14. So that's going to put me somewhere around, somewhere about here. And then if I add 14 to 108, that gets me 122, somewhere there. So if I say that the true mean lies somewhere between our sample mean plus or minus 2 standard errors, I'll be 95%, roughly 95% certain the true mean lies in that range. And in fact, you see that's exactly the case. You know, our true mean is right there. So this is how we express the uncertainty for multiple sample experiments. You take the sample mean and you add in plus or minus roughly 2 standard errors of the sample mean, and then you can be about 95% certain that the true mean lies somewhere in that range. And that's because if you take a lot of sample means, you run the experiment many different trials, and you plot that out, that gives you a normal distribution. And the average of those sample means will be the true mean if you have many different measurements, and then the distribution will be related to the standard error. Okay. So I've written this down, and I'll just repeat myself here. So for typical engineering applications, we want to have a confidence interval of 95%. We just want to be 95% certain that our reported measurement contains the true mean. So again, for 95% exactly, it's plus or minus 1.96 standard deviations. So you can see here, 2 standard deviations is 95.4, so 1.96 is actually 95%. It doesn't matter whether you use 2 or 1.96. They're both close enough. And so our true mean, mu, is our sample mean, is going to lie in the range of our sample mean minus 1.96, our standard error. And on the upper bound, it'll be our sample mean plus 1.96 times our sample, our standard error. And then oftentimes we'll put in parentheses 95% CI to indicate that we're talking about a 95% confidence interval. A lot of times people won't put that parentheses 95% confidence interval because that's the default for engineering. If you use something other than 95%, let's say you wanted to be 99.7% confident, then you do the plus or minus 3 standard errors. And then it would be a good idea to put it in parentheses here, 99.7% confidence interval, so everyone knows you're not using the default. You're using something else. So another way to express it's over here. This is the same expression as this one on the left. It's just written in the plus or minus format. And then here what I've done is I've just substituted in for the standard error. So just take your sample mean, which is this measurement we did right up here, plus or minus 1.96 times the sample standard deviation, which was this one right here, divided by the square root of the number of samples used to get that sample standard deviation. And then again, if you want to be thorough, you can put the 95% confidence interval so everyone knows what that confidence interval is. So our mean value, a true value, should lie somewhere in that range. It's not guaranteed. Remember, we're only 95% confident, so it's possible that the real measurement could be outside that range. It's very, very unlikely, but it's possible, so you just have to keep that in mind. Now, this expression that I have here on the screen is really only true, it turns out, if you have many measurements. More than about 30 measurements, it turns out. When you have fewer than 30 measurements, then the distribution of the sample means isn't exactly perfectly normal. It's a little bit different from normal. And statisticians have figured out a way to account for that, and we use what's known as a t-factor. It actually becomes what's called a student t-distribution. And there's a t-factor. It's basically a correction factor that you should take into account when you have a small number of measurements. So that's given down here. What we have here is the number of measurements you've made, and then the t-factor. Let me just focus on this part of the expression so it's just easier to deal with. In that case, what you do is the true mean will lie within the sample mean plus or minus this t-factor times the sample standard deviation divided by the square root of the number of measurements. And this is for 95% confidence interval, because this t-factor is specifically for 95%. There are other t-factors for different confidence intervals, but I'm just showing the one for 95%. So if I had 5 measurements, I would then use a t-factor of 2.78. Rather than using the 1.96, since I have such a small number of measurements, I should increase my kind of range within which the true mean lies by a little bit according to this t-factor. So I should use 2.78 rather than 1.96 here. In my particular case, here we had our 7 measurements. Our t-factor is 2.45, and you can see that right here. So in our particular case, our sample mean was 108. Sample standard deviation was 18.5. Our t-factor from this table is 2.45. So our measurement, you can see the t-factor right there. Our true mean will lie within 100. It'll be 108.44 plus or minus 17.12. That's just this term. To within 95% confidence. Our true mean will lie somewhere within that range. Another way to express that is down here. You just you actually do the minus and the plus here, and you can see our true mean based on these 7 measurements. And again, let's just pretend we're measuring temperature. I make 7 temperature measurements, And from those 7 measurements, I can say that the true temperature of our actual cavity that we're measuring the temperature of, we're 95% certain its temperature is between 91.3 and 125.6. Just based on our measurements, that's as good as we can get on our prediction. Okay, it lies somewhere within there, within 95% certainty. Could lie outside, but it's very, very unlikely. Okay. One other thing about this t distribution factor, I said that you need to have more than about 30 measurements before we can ignore the t factor. And you can see that when you have 30, as you increase the number of measurements, you're getting closer and closer to this value of 1.96. And if you had an infinite number of measurements, it would be exactly 1.96. So the rule of thumb is once you're above about 30 measurements, or 30 samples, just go ahead and use the 1.96. You're close enough. Okay. But below that, you should use this t factor to try to increase the range of your bounds for your true value estimate. All right. And so I just tried to show this graphically over here. We already kind of talked about it. So if I just went to 91 point, actually this picture got all messed up. Must have moved around. So we were saying that our true measurement, our true mean lies somewhere in this range based on our uncertainty analysis for our multiple sample experiment. So let me ask you a few questions here. First of all, what happens as the number of measurements increases? So we have here, what happens as the number of measurements increases? Well, it turns out that our range here will get smaller and smaller. Remember that the standard error, let me go back to that. The standard error, if we increase the number of measurements, that means the n increases, and then our standard error gets smaller and smaller. We will know the true mean value more accurately. We'll be closer and closer to the true mean because we've narrowed the distribution of our samples has gotten tighter and tighter. So what happens as the number of measurements increases? We'll end up getting closer and closer to the true value. So as n increases, the standard error decreases. So our range of uncertainty gets smaller. What happens as the sample standard deviation increases? So this is this value here, the S, or our variance. Basically what it's saying is what happens if the scatter in those measurements gets smaller. So they're all closer to the same value. They're not as widely spread out. So what happens in that case? Well, in that case, if we have a smaller sample standard deviation, it will also give us a smaller standard error. Remember again that the standard error, I'll write it over here, is the sample standard deviation divided by the square root of the number of measurements. So if the standard deviation goes down or the number of measurements goes up, our standard error gets smaller. And remember that standard error is this quantity that I'm highlighting right here. That's our standard error. So that affects our plus and minus values. So if we can make that smaller, we have a better estimate of what the true mean is. So that's a goal when you run the experiments, is ideally the more trials you run, the better off you're going to be. Or if you can somehow figure out a way to reduce that scatter, you're going to be better off as well. It kind of makes sense. The more information you have, the better prediction you can make, and the less scatter you have, the better your prediction is going to be. Okay, so the next question, what's the difference between the sample standard deviation and the standard error of the sample mean? You know, the wording is very precise here and gets kind of confusing. The sample standard deviation is related to the scatter in the experimental measurements in your trial. So that's just related to the scatter in these measurements. That's the sample standard deviation. The standard error of the sample mean is related to the distribution over here. Remember that this plot is showing on the horizontal axis, these are the values x bar. These are if I could run this experiment many times, okay, many different trials, 7 measurements in each trial, and I plotted out what the sample mean was in all of those cases, I would get this curve in these blue things here, right? That would be the distribution of my sample means, and the standard error is a measure of the breadth of that curve. So that's how that works. If I made more measurements per trial, so instead of 7 measurements per trial, if I had 100 measurements per trial, the breadth of this curve would get smaller and smaller and smaller, because all of my sample means would approach one another, and they would all get closer and closer to the true mean in that case. Same sort of thing if I had a smaller standard deviation for each trial, then all the sample means would get closer and closer to one another, because there's just less scatter in each measurement, and they would all approach the same values, and they would get closer and closer to the true mean. So the standard error of the sample mean is just a measure of this distribution's breadth, and the goal is to make that narrower and narrower so we get a more accurate reading of the true mean. So so that's talking about how to express the uncertainty in a multiple sample experiment. The way we do it, just as a refresher, is we say our measurement is the sample mean plus or minus this t factor, typically at a 95% confidence level, multiplied by the standard error, which would be the sample standard deviation divided by the number of, let me change the way I'm writing that. The sample standard deviation divided by the number of samples that we've measured. And if you want, you can put in the parentheses 95% confidence interval. That is how we express excuse me, our uncertainty for a multiple sample experiment. So it's a lot more complicated than the single sample case, the single sample experiment. So multiple samples, you have to rely more on statistics and probability to get how the best way to express that uncertainty. So just remember, ultimately, this expression. All the statistical part that I've just talked about is just more for background material. You don't have to remember all that. What you really need to remember is that expression here. Okay. And again, if n is greater than about 30, then just make t 95%. 1.96 or equal to 2. They're both close enough. Okay. All right. Let me move on to a different topic. It's related, but a little bit different. In many cases, when we make measurements from an experiment, ultimately we want to get some relationship. Right? We do a curve fit to that experimental data, and that's what I've shown here in this plot. What I did is I used Excel. We have some x values here along this axis, and then I just had some y values here on this axis, and these are all the dots. The dots are my experimental measurements, right? And I want to get a relationship between x and y. You've done this sort of thing before in Excel. You can plot a trend line that fits to the data. That's shown here. So Excel will do what's called a least squares regression. It's outside the scope of this course, but it does a best fit to the experimental data. And here we can see the equation of a line. That I tried to fit it with a line. And you can see the slope and the intercept. So the intercept here, and then the slope would be here. The r squared is called a coefficient of determination. It just tells you how good your curve fit is. It'll have a value between 0 and 1. The closer you are to a value of 1, the better your fit. So here we have a value of 0.9962. We have an excellent fit in this case. You typically want that r squared to be in the 90s, certainly, and the closer you are to a value of 1, the better. So one question I have is, we fit this. You can see that the fit isn't perfectly in line with all the points, right? The points kind of lie off a little bit from the line, so it's not a perfect fit. It's pretty darn close, but it's not perfect. So one question is, what is the uncertainty on the least squares curve fit, slope and intercept? What you'll do when you do a curve fit in Excel, this linear regression, it'll spit out the numbers for the slope and the intercept. But what's the uncertainty on those values? Well, the uncertainty on that will be the slope value plus or minus the 1.96, we know this from our previous discussion, times the standard error for the slope. And similarly for the intercept, it'll be intercept value plus or minus 1.96 times the standard error for the intercept. So in order to get the uncertainty for the slope and the intercept, you need to know those standard errors. Well, how do you get that? Well, it turns out you can actually get it from Excel using the linest command, or linest command. And you'll just have to look at the documentation for Excel to do that. But if I call this column A over here and this one column B, and this is row 2 all the way down to, what is that, row 15. The way you can use this linest command, it looks something like this. Again, you just have to read the documentation to get what each of these terms represents. But it'll give an Excel output. It's actually an array formula, and it'll give an output like this. The format of this data is it'll give you the fit value for the slope. That's the 4.98 right up here. It'll give you the fit value for the intercept, which is this one. Then the next two items, the next row down, these are the standard errors for the slope and the intercept. So these are the standard errors that you would use up here. So you can get this information from Excel. And then there's some other statistical information that we won't worry about. You can ignore these things. They're not useful for us at this point. So that's the way you can do it in Excel. And then I've actually also written a Python script to do these kinds of calculations also. So the Python script, what it does is it'll read, well, here I've put the data, I've just taken this data here, and I've just directly programmed it into my Python code. But you could imagine reading in a data file instead. And then in here, this function is the equation I want to fit the data to. You can see it's the equation of a line where the parameters that I'm trying to determine are right here, M and B. The X is this array, our X values. So I'm trying to fit to this curve fit. The nice thing about this Python script is you don't have to use an equation of a line. If I could put any function in here. So I can put any function in this Python code. I don't just have to use straight lines or polynomials. I can put whatever I want here, and it'll do the best fit to those parameters. And then within Python, there's this function that does the optimization, tries to adjust the parameters such that it finds the best fit. Again, you just have to read the documentation on these things. And then here I just have it specify what the values are for the best fit parameters, as well as what the standard errors are. And then I plot, the rest of this is just plotting. So if you ran that Python code, it'll spit out the best fit value for the slope and the intercept, what the standard errors are, they match what Excel has, and then I also have it actually plot the data in the curve fit and gives the parameters there. I've just learned how to program in Python, so you might find a better way to do this program. Maybe there's an error there, I don't think there is, but you're probably a better Python programmer than me, so you might find a better way to do this. But if you want to know how to do these things, you have to read the Python documentation. I just wanted to give it here because in a lot of the labs that you'll do, you need to do curve fits to some of the data. And this is how you get the uncertainty to the parameters in those curve fits. And that uncertainty is useful for propagating the uncertainty along into other calculations. Okay. Now, I know I'm running long on this lecture, but we're just going to continue on to get all the material in. You can always pause it, go get something to eat, go get something to drink, and then come back or just look at it a different day. So I'm going to continue on. So next question, or next comment I have is really, what's the difference between histograms, frequency distributions, and probability distributions? I've actually used all three of those terms earlier in the lecture, and I didn't really explain what they are. So let me go ahead and describe them here. All three are a little different. So a histogram is what you might be most familiar with. In fact, I'm certain you're most familiar with histograms. A histogram plots the number of samples within a specified size bin. So what I did is I generated some data. It has values, the values are given here. And then the vertical axis here on this histogram just tells me how many of those samples have that particular value. So for example, let's just focus on the blue curves. So for values of between, I think that's what, 95 and 105, I've got roughly, I don't know what that is, about 28 values in that range. And then between 120 and 130, I've got 15 values in that range. So that's what a histogram is. Just kind of gives you the number of counts, you know, the number of values within a certain range. There's a bin size here. If you look at this for a second, just focus on the blue. You know, for the blue here, the bin size is between 120 and 130 here. So there are, again, 15 samples or 15 measurements that have a value between 120 and 130. So that's what a histogram gives you. Now, what you'll notice in this plot is that I've done the histogram using one bin size that corresponds to the blue here. Those have a value of 10 in terms of the bin size width. And then I did it again in this orange histogram where the bin size is half the size. So the bin size there is 5 instead of 10. And one of the things you'll see is that the histograms clearly look different. Right? The orange histogram has smaller values than the blue ones, and that's because I've got twice as many bins, and so I just have fewer counts in each bin. That makes sense, right? So one of the things with histograms is that the plot will change depending on the bin size, as you can see here. Right? So histograms change depending on your bin size. In addition, if I integrated the area underneath that curve, it would not be equal to 1. It'd be some other number. So there's no kind of consistency from one histogram to the next. Now, generally, we prefer to have that kind of consistency. It's just better. The more things you can make the same from when you're comparing two things, the better off you are. Right? If everything's changing from one plot to another plot, it's just hard to do a comparison. So histograms are easy to make, but they have some flaws. They change depending on their bin size. They're just not ideal. So what is typically done is modifying that histogram to what's called a frequency distribution. Now, a frequency distribution tells us the fraction of samples in a certain size or certain bin size range. And so the way to think about this, so when I say fraction, it's not the total count. Let's say, let me go back up to this histogram. And let's say that the total number of measurements here was, I don't know, 200. Right? So here I have 50, and let me change that. Let's say the total number of measurements is 150. Okay? So if I add up the number of counts for each one of these blue bins, let's say it all adds up to 150. So here for this bin it was 15. So the fraction of measurements in that range would be 10%. Be 15 divided by 150. So that's what a frequency distribution does, is it gives us the fraction. It tells us what fraction of the entire set of measurements lies in a certain range. So let's look over here on this plot. So here what we have is our value again, same sort of range that we have on the values up there. And now I have frequency over here. Ignore for a moment the, ignore this part for a moment, the 1 divided by value. And let's just focus on the black line with the circles. Okay, so here is this plot here, the black dots actually is the frequency distribution corresponding to the blue curve. So what I've done is I've converted my histogram to a frequency distribution. Excuse me, and that's these black dots. Okay, so when I talk about the frequency distribution gives us the fraction of samples in a certain size range. It's the area under the curve in that size range. What it means is if this is my frequency distribution, that's this axis. If I take the frequency and I integrate from whatever, x to x plus delta x, whatever range that is, that'll give me, this is incorrectly written, this will be equal to the fraction of samples in that range. Right? The fraction of the samples in that range is equal to this expression down here. So what that means is if I go back up in here, if I wanted to know the fraction of samples between this point and this point, actually, you know what? Let me use some more well-defined numbers. So let's say 80 and 100. If I want to know the fraction of measurements in that range, I would just find the area under this curve. And this will be the fraction of measurements or samples between or with values between 80 and 100. So you can see, for example, I'll have a large number of measurements between 80 and 100, but I'll have very few measurements between that point and this point. Right? Most of my measurements are somewhere in this range. And when I say fraction, the value goes between 0 and 1. If I integrate all the way from 0 up to infinity, from minus infinity to infinity, the fraction would be equal to 1. All of my measurements lie within that range. So the area under the frequency distribution is always equal to 1 because 100% of the measurements lie within the whole range. So that's this comment over here. The area under the curve is equal to 1. It's always equal to 1. Unlike the histogram, when you look at the area under the curve there, it just varies depending on your bin size. For frequency distribution, it's consistent. The area under the curve is always equal to 1. Okay. The other nice thing about frequency distributions is they're insensitive to bin size. Okay, so now up here in the frequency, in the histogram, you can see that the two histograms here are different because I use different bin sizes. But down here, let me erase some stuff. What I've done is I've used two different bin sizes here. The black line corresponds to the same bin size as the blue up here, and the blue dashed line with crosses is the bin size corresponding to the orange case. But you'll see, even though they're a little different, they're insensitive. They're much closer together. You don't have the same height differences that you have in the histogram. With the frequency distribution, they're much, much closer to one another. So the frequency distributions are a lot more consistent. They're not sensitive to bin size. So it's nicer to work with frequency distributions because they have a good physical meaning. The area under the curve is related to the fraction of measurements within that range. And they're less sensitive to bin size. The way you get a frequency distribution is shown here. So the frequency within a particular size range, actually this is a mistake the way I've drawn this here. This should be frequency within xi and within this range. Sorry. Between xi and xi plus delta xi. So within some range, the frequency within that range will be 1 over the bin size, that's the delta xi here, times ni. This is the ni is the number of samples in the range xi plus delta xi. So this is like this comes from our histogram. The ni is this number, like 15 here. So the ni in the bin xi here would be 120, the delta xi would be 10, and the ni would be 15. Okay? And then capital N is just our total number of measurements. It would be like if I added up all of the measurements I did, like in the previous example I said I think there was 150 total measurements. That's what the capital N would be. And that would give me the frequency point to put, on this location right here. Okay, so that's the frequency distribution. And in practice, it's just, it's better to work with frequency distributions as opposed to histograms for the reasons I talked before. They're insensitive. The bin size, the area underneath the frequency distribution is always equal to 1. Just a little more consistent. And then the last thing that I talked about in our lecture is the probability distribution. A probability distribution is just a frequency distribution, but we have a huge number of samples. You can see, for example, our frequency distribution here, it's kind of jagged. If I got more and more samples, instead of 150 samples, I had 10 million samples, just a huge number, then it would smooth out and produce what's called a probability distribution. A probability distribution has all the same traits as the frequency distribution. It's just you have a lot more samples and it makes it smoother. So actually these three plots that you see, the histogram, frequency distribution, again, these are based on the same data. The blue data here in the histogram are the black dots in the frequency plot. The orange histogram are the blue dashed line. They're using the exact same data. And then what I did is I actually took a lot more samples and plotted the probability distribution. And so you can see that's, if you took a huge number of samples, you'd get the kind of reddish curve here. And so you can see my frequency distribution, I just don't have enough samples in it to reproduce the true probability distribution. The more and more samples I took, my frequency distribution would adjust and it would actually start to follow that red line more precisely if I just had more samples. So that explains the difference between a histogram, a frequency distribution, and a probability distribution. It's just for your own benefit, just so you understand the difference in the terminology. Now, the very last thing I'll talk about is how do you know if your data is normally distributed? So one of the key things in this whole discussion is we said that truly random uncertainty fits a normal distribution or a Gaussian distribution. If you plotted all the results that you got from your measurements, it would follow a normal distribution. How do we know that our measurements truly follow a normal distribution? Well, there are different tests that you can use to give you confidence that it follows a normal distribution. You never truly know, but you can be pretty confident. So one way you could do it is just a qualitative comparison of just plotting a normal distribution fit to your data. So here's our histogram of some data. And we talked about what a histogram is. So here's what it looks like. If we're going to see if it fits to a probability distribution, what we should do is convert it to a frequency distribution. So that's the black dots. So I just took that histogram and I converted it using this formula here. And then I got these black points. And then I took the mean value of these black points and the standard deviation of it. So that's the sample mean and the sample standard deviation. And I plotted a Gaussian or a normal distribution using that same mean and sample standard deviation. And that's what the normal distribution looks like. So then you could say, well, does that look like a Gaussian? Is the black data Gaussian? Is it or isn't it? It's kind of tough to tell, right? I mean, it sort of looks okay, but I don't know. It's tough to tell. It's very much a judgment call. Two different people might say two different things. So, doing a qualitative comparison is not recommended. You just can't tell. A better way is to do what's known as a normal QQ plot or normal quantile plot. This is a little better way to do it. It's still a qualitative comparison, but it does give a better visual check. And the way these plots work is it does a comparison between your data and a normal distribution. And I won't get too much into the details of it, but we know from a truly normal distribution that if I look at this plot here, 0.1% of the data will lie below the mean value minus 3 sigma. You can kind of see it in this plot. So 0.1% of the data should lie below that. 2.2%, so this 2.1 plus 0.1 will lie below the mean value minus 2 sigma, and then so on and so forth. So we kind of know how much data should lie below these values, right? And so we know what it should look like for a normal distribution. We can do the same idea for our actual data. What fraction of the data lies below a certain value? Okay, those certain values are called the quantiles. Okay, that's where this comes from up here. Okay, so this is why it's the quantile plot, or QQ, quantiles for the normal distribution, quantiles for the actual data. And you plot those out, and this is what a QQ plot looks like. So on the horizontal axis are the theoretical quantiles. These are basically the standard deviation. So here's the mean value, -1 standard deviation, -2, and then these are the plus values. And we know how much data should lie below those values. And then these are the actual values from our actual data set, the sample quantiles. These are from our data set. And if you look up here, here are our values. So we'd expect roughly half the values to lie between. Our mean is somewhere close to 100 here, we would estimate, right? Looks like it's pretty close to 100. So here you can see, yeah, that corresponds to about 100. So anyway, it plots the what fraction of the data lies below our quantiles for the samples, what fraction lies below, from the actual theoretical distribution. And it should follow a line on here. So you can see our actual data is pretty close to that line. It's not perfect, but it's pretty close. But you can see much better qualitatively that, yeah, this data looks like it's actually following a normal distribution. If it was a normal distribution, it'll follow that line precisely. So unlike this plot here, where you're just saying, well, it looks kind of close, I'm not positive. This is really tough to tell qualitatively, but this plot is much easier to tell qualitatively. It looks like a normal distribution. So does the data follow a normal distribution? Mostly. So yes, mostly. Where does the data deviate the most from a normal distribution? It seems to deviate the most at the tails. At the tails of the distribution. What I mean by that is out in these regions. The data just doesn't follow the normal distribution quite as well there. And you can see that because we get the most deviation from the line at that point. In the middle, it's doing a pretty good job. Right? So that's what a QQ plot does, is it gives you a quick visual representation of whether or not your data is normal. And if it is normal, it'll follow that line. It's still a qualitative check. You still have to kind of make a judgment call, but it might be an easier judgment call. The last way you can do it is to use what's called a goodness of fit test. And there are a variety of these. These are quantitative assessments. So these are the kind of if you really want to know for sure if your data follows a normal distribution or not, these are the tests to perform. And one that's highly recommended is the Anderson-Darling test, and it's just named after the researchers back in the 1950s who came up with this test. It's kind of complex. It's heavy into the statistical stuff, so I'm not going to present the details here. It's out of scope. Basically, it just checks numerically whether the sample data follows the expected normal distribution. It looks at the difference between the normal distribution and the actual data and does some quantitative calculations based on that. Obviously, it requires a more advanced knowledge of statistics to apply and understand. It's not the only kind of quantitative test that you can use. There are others, like I list here Shapiro-Wilks, Kolmogorov and Smirnov test, and then the skewness-kurtosis test. These are all just different techniques to check. None of them are perfect, but they certainly do a better job than the qualitative checks. And they'll just tell you with 95% certainty whether or not your data follows a normal distribution or not. And they can actually be used for other kinds of distributions, not just normal distributions, but maybe log normal or exponential, just other kinds. So we won't get into the details of that. Being able to check whether your data is normal or not, this is just kind of bonus material. You're not going to have to do this in this course, but since so much relies on knowing that our data follows a normal distribution, it's probably a good idea if you're doing some critical work just to verify that you have confidence that your data is following a normal distribution. And these are the ways to do it. And if you want to see how to run these tests, I actually, again, give some Python code to do these checks. And again, I'm not a good Python programmer, so you could probably do this better. But here you can read in a data file, calculate the mean and standard deviation as well as the number of entries, plot a histogram. So here's how you plot a histogram of the data. Here's how you produce a frequency distribution of the data. There's actually a function called histogram that if you set density equal to true, that actually produces a frequency diagram. If density was false, it produces a histogram, If it's true, it produces a frequency plot. And then here's a plot just showing whether or not, showing well, this one does the plot of the frequency distribution. This is a plot showing the normal distribution. That part of the code just produced this plot. And then if you want to produce the QQ plot, that's just a simple command. QQ plot, and you put in my data, and that'll produce this plot here. And then if you want to do the Anderson-Darling test, that's given down here, but that's more advanced. You don't have to worry about that. But if you run that code, this is the kind of information you'd get out of it. The Anderson-Darling test, what it does is it actually checks different parts of your data set to see whether or not each part follows a normal distribution. So you'll see that this says the data does indeed follow a normal distribution over several different parts of the curve. So you're pretty confident that the whole curve follows a normal distribution. All right, and then I give a few references here if you want to learn more. It's all measurement uncertainty is a huge important topic. There's a lot of research being performed on it right now. So there's a lot of study of the topic, especially for trying to estimate the uncertainty in very complex situations. Let's say you have a computational fluid dynamics program, a numerical way of solving fluid dynamics problems. Lots and lots of calculations. There's research on how best to estimate the uncertainty for those calculations. So a lot of research on the topic, and it can get pretty statistics heavy. So I've covered a lot. This lecture is kind of long. Let me just review the important parts for you. First of all, important part number one, I would say, is, let me just go all the way back up to the top. Important part number one is you should just realize that every measurement has uncertainty to it, and that you should always try to report the uncertainty in a measurement. One of the most common issues we have with graduate students when they do research is they'll present some experimental data or even computational data, and they won't have any discussion of uncertainty. And what we do is we send them right back to the lab to figure out the uncertainty analysis, because you have to report the uncertainty in any measurement. Okay, so always keep that in mind. You really need to report uncertainty with your measurements. The other thing I want you to remember is we have blunders, systematic uncertainty, and random uncertainty. Blunders you can avoid through careful planning. Systematic uncertainty you avoid through calibration. Random uncertainty you kind of have to live with, but we can quantify it. With single sample experiments, we quantify the uncertainty as plus or minus 1/2 the least count. And the least count should be based on what you have 95% confidence in when you do the least count. So use the stopwatch example as an example of that. Even though a stopwatch can go out to 1/100th of a second, you can really only, with confidence, get a measurement to 1/10 of a second. So your least count in that case would be 1/10 of a second, and your uncertainty would be plus or minus 1/2 that least count. So that's how you deal with single sample experiments. Oops. With multiple sample experiments, it gets more complicated, but in the end, the only thing you need to really know is we report the uncertainty for those as the sample mean plus or minus this t factor times the standard error of the sample mean, which is just the standard deviation, sample standard deviation, divided by the square root of the number of measurements. And if you have a bunch of measurements, more than about 30, you can just set that t factor equal to 1.96 or 2. So that's all you really need to know. I went into a lot of detail here, but this is ultimately what you need to know for that part. If you're dealing with curve fits, those also have some uncertainty, and you can get that uncertainty through some a little deeper analysis of your curve fitting program, but that uncertainty will be, again, a plus or minus 1.96 times the standard error. You get the standard error from whatever program you use to get the curve fit. And I give both an Excel and Python case to kind of show you where those come from. Difference between histograms, frequency distributions, and probability distributions. All I'll say about that, you don't need to know a huge amount of detail, but the preferred way to present data is actually with frequency distributions and not histograms. Histograms are just kind of a quick way to present data, but the preferred method is actually to use frequency distributions. So think about trying to present your data in terms of frequency distributions. And the way you find them is from this formula down here. And then as far as checking for normality, that's just really bonus material. But if you're dealing with kind of critical calculations and you really want to just verify that your data is normal, there are tests for checking that. And an easy qualitative way is to do these QQ plots. Just you can visually do it, and it's easy to code in. But if you really want to do it right quantitatively, you have to use one of these goodness of fit tests like the Anderson-Darling test, the details of which are outside the scope of this course. So a lot of information in this video. It's jam-packed, but your application of uncertainty in this course will be, we won't go through any more of the statistics of it. The lecture here is just background material, but your actual application will really primarily focus on reporting the uncertainty either in this manner or using the single sample, plus or minus 1/2 the least count. So that's really your application will be. The other thing that you'll do quite a bit of will be covered in the next lecture on propagation of uncertainty. So once we have the uncertainty in these measurements, how does that uncertainty propagate into a calculation? So let's say, for example, I have the ideal gas law, and I make a measurement of the pressure and the temperature, and I have some uncertainty in those measurements, and I want to calculate the density. How does the pressure uncertainty and the temperature uncertainty produce uncertainty in the density calculation? So that's going to be the topic of the next lecture. So you'll do a lot of that actually in this course. All right, we'll go ahead and end it there.